The art of algorithm analysis, decoding efficiency in code. In the world of algorithms and programming, efficiency isn't just a buzzword, it's the cornerstone of performance-critical applications. Whether you're optimizing a search engine, building real-time data processing systems, or developing machine learning models, understanding how your code behaves under different inputs is crucial. Algorithm analysis provides the tools and techniques to evaluate time complexity, space complexity, and overall scalability of algorithms before they ever touch production environments. This guide dives deep into these principles, offering both theoretical foundations and practical examples that every developer should know. Why algorithm analysis matters. At its core, algorithm analysis helps us understand how well our solutions perform. It allows developers to make informed decisions when choosing between competing implementations, ensuring optimal resource utilization and system responsiveness. An effective algorithm can transform a sluggish application into a blazing fast experience. For instance, using a binary search instead of linear search reduces lookup times from O(n) to O(log(n), making significant differences in large datasets. Real-world impact. In web development, inefficient sorting routines could lead to noticeable delays during user interactions. By analyzing algorithms beforehand, we prevent such bottlenecks and ensure smooth user experiences across platforms. Fundamental concepts in algorithm analysis. Before diving deeper into specifics, let's establish some foundational knowledge. Time complexity measures how execution time increases with input size, while space complexity evaluates memory usage trends as data grows larger. Big O notation serves as the standard language here. It abstracts away constants and lower-order terms, focusing solely on asymptotic behavior, how functions behave as inputs approach infinity. Example: an algorithm with O(n) superscript 2, complexity will take significantly longer than one with O(n) log n, for very large values of n, even though their actual runtime might be similar for small cases. Understanding these fundamentals equips programmers to choose appropriate data structures and design efficient operations tailored towards specific problem domains. Time complexity explained. Time complexity quantifies computational effort required by an algorithm relative to input size. Common classifications include constant, O(1), logarithmic, O(log(n), linear, O(n), quadratic, O(n) superscript 2, exponential, O(2 to the power of n), and factorial, O(n). Evaluating an algorithm involves counting primitive operations rather than exact clock cycles, since hardware variations affect absolute timing measurements. Focus remains on growth rates compared to other algorithms. Categorization examples: O(1) accessing array elements at known indices, O(log(n) binary search implementation steps, O(n) iterating through each element once, O(n) log(n) efficient sorting algorithms like merge sort, O(n) superscript 2 nested loops common in matrix multiplication, O(2) recursive problems without memoization. Recognizing which category applies ensures better choices regarding scalability expectations and maintenance requirements over time. Space complexity considerations. While often overlooked, space complexity plays a vital role in determining program feasibility, especially within constrained environments like mobile devices or embedded systems. This metric considers not only auxiliary storage but also input size itself. Algorithms may require additional working memory proportional to input dimensions. Difference between space-time trade-offs. Some methods sacrifice extra memory usage to achieve faster execution speeds, a classic example being hash tables versus binary trees for lookups. Managing memory efficiently becomes critical when dealing with huge files processed sequentially without loading entire contents into RAM simultaneously. Analyzing specific scenarios. Let's explore concrete scenarios where careful algorithm selection makes all the difference. Imagine handling social media feeds requiring frequent updates based on user activity logs. A naive solution would recompute feed rankings entirely after every update, resulting in poor scalability due to repeated full recomputations. A smarter approach uses incremental updates, maintaining previous state information smartly. Alternative approach. Implementing change detection mechanisms allows updating affected portions only instead of rebuilding everything anew, an elegant way reducing overhead considerably. Such optimizations become essential features whenever real-time interaction demands high-throughput capabilities alongside low-latency expectations. Misconceptions about performance metrics. Many beginners assume smaller Big O numbers always translate directly into faster programs regardless of context. However, hidden constants matter greatly too, despite being ignored formally in asymptotic notation. Hidden constants example. While bubble sort has worst-case complexity than quicksort, for tiny arrays, benchmarking real implementations against synthetic tests reveals nuances missed purely through theoretical comparisons alone. Practical testing complements mathematical analyses effectively. It's crucial to balance analytical rigor with empirical validation whenever possible to avoid premature optimization pitfalls. Tools and techniques for profiling. Modern IDEs integrate profiling tools helping identify performance hotspots easily. These range from built-in debuggers showing function call stacks down to specialized profilers tracking CPU/memory consumption patterns. Common tools include Visual VM, Java Profiler providing heap dump analysis, gprof, C/C++ prof toolset measuring function calls perf, Linux command line interface for CPU sampling, JMeter. Load testing framework simulating heavy traffic conditions, Valgrind. Memory leak detector useful for debugging issues related to incorrect allocations/deallocations. Leveraging these utilities enables precise identification of slow parts needing improvement while avoiding unnecessary changes elsewhere that wouldn't yield substantial gains. Design patterns for optimal execution. Several established software engineering practices enhance algorithmic efficiency naturally. One prominent pattern revolves around divide-and-conquer strategies, breaking complex tasks into manageable subproblems recursively solved independently. Divide-and-conquer benefits: reduces redundant calculations via caching intermediate results, distributes workload evenly among parallelizable components, enhancing multi-core processor utilization. Other notable patterns involve dynamic programming, storing previously computed states, preventing recomputation waste seen frequently in recursive formulations lacking memoization. Choosing suitable design paradigms upfront influences maintainability aspects equally, if not more, than raw speed improvements themselves. Challenges faced during implementation phases. Even theoretically sound algorithms sometimes falter upon translation into actual code due to various reasons ranging from improper variable scoping up to subtle bugs causing infinite loops unexpectedly. Implementation pitfalls: off by one errors leading to incorrect iteration ranges, incorrect base case definitions, altering recursion tree depths, data type overflow causing unexpected result truncation, inadequate error handling disrupting flow control logic, overlooking edge cases producing invalid outputs, silently rigorously unit testing every component separately along with integration test suites minimizes chances encountering such anomalies post-deployment phases. Automated regression tests further safeguard existing functionalities against regressions introduced accidentally during future enhancements. Emerging trends influencing algorithm design as computing landscapes evolve rapidly, driven by cloud infrastructures and AI advancements. Traditional algorithm evaluation criteria face new challenges demanding fresh perspectives. New frontiers, quantum computing introduces fundamentally different ways evaluating algorithm efficiency, potentially rendering classical metrics obsolete and less adapted accordingly. Distributed architectures shift emphasis from single-threaded efficiencies toward network communication costs, becoming dominant factors affecting total operation durations now. Adapting current methodologies means embracing probabilistic approaches, accounting uncertainties inherent within decentralized systems operating asynchronously over unreliable networks. Best practices for writing maintainable efficient code. Efficiency doesn't merely mean writing the fastest possible code, it also entails crafting readable, maintainable versions others can understand later. Following clean coding standards facilitates long-term project sustainability. Code quality guidelines. Use descriptive names conveying purpose clearly, keep individual functions focused, performing singular responsibilities, implement defensive programming techniques, anticipating potential failure modes, gracefully document non-obvious logic, explaining why certain choices were made, refactor regularly, eliminating duplicated efforts, improving clarity, progressively combining these habits leads to robust solutions, balancing performance needs with human factor considerations. Integral to collaborative software development workflows. Version controlling all iterations enables tracing back historical modifications, reverting any problematic alterations safely without losing progress unintentionally. Measuring success beyond traditional benchmarks, evaluating algorithm effectiveness shouldn't rely exclusively on conventional performance indicators anymore given modern computing realities. User satisfaction scores offer alternative quantitative assessments reflecting real impacts accurately. User-centric evaluation criteria. Response time thresholds below which users perceive lag error rate percentages indicating reliability levels achieved, practically saturation points beyond which additional resources provide diminishing returns, throughput capacities measured against expected request volumes, resource contention indicators revealing bottlenecks emerging, dynamically integrating telemetry frameworks collecting end-user feedback automatically allows continuous refinement aligned closely with operational goals defined originally. Prioritizing measurable outcomes ensures alignment between technical achievements accomplished internally and tangible benefits realized externally, facing customers actively utilizing delivered products/services daily. Conclusion: mastering algorithm analysis empowers developers to create scalable, efficient, and reliable software systems. Understanding time and space complexities forms the foundation for selecting appropriate algorithms and data structures tailored specifically to particular use cases. By combining theoretical knowledge with practical experimentation using profiling tools, engineers gain confidence in making informed trade-off decisions impacting overall product quality positively. As technology continues evolving rapidly, staying updated with emerging trends remains essential for continued success in competitive markets today.